Hello and welcome to this revision session on practical skills for A-Level Physics Paper 3 for the AQA specification. So we're going to be looking at the key content regarding practical skills which could be examined on the AQA A-Level Physics Paper 3. So the first area we're going to be looking at is experimental design. So it's a common examination question to ask students to write an experimental method to derive a particular value or set of values. So to carry out this task you need to split your response into three sections. Section 1 is looking at independent and dependent variables. So identify the independent and dependent variable in your investigation. State how each variable will be measured with the correct measuring device, and then state the range and the interval of the independent variable for the investigation. Now it's important to note that the range of the independent variable must be as large as possible while still being safe to carry out the experiment. Now the experimental range is the set of values for which the conclusion, the trend, the values that you calculated are valid for. So the interval of the independent variable should give at least 5 values for the dependent variable in your experiment. Now this will allow for a line of best fit or a trend to be established easily. Now the second section is regarding experimental technique. Now in this one, identify any control variables and how they will be controlled. Identify any way the experimental technique can be modified to reduce uncertainty. Think of a discussion about carrying out repeated measurements and calculating averages if appropriate. Now measurements should be repeated until concordance is achieved with values. Now at GCSE you said to repeat until 3 times. At A level it's actually until you achieve concordance, consistent results each time. So repeated readings until consistent results are achieved reduce the random error of your results. And the third section you would include in your write-up is the graph. So state the graph that will be drawn from the experimental data gathered. If you need to derive a value from a graph, look at the ways in which the y-axis and the x-axis values can be adjusted to get a straight line of best fit. Then you can put the experimental equation into the form of y equals mx plus c, and then you can work out your wanted value. So thinking about your 3 sections, you've got your independent and dependent variables, your experimental technique and your graph. When you're writing your answer, split your answer into the paragraphs, each addressing the different parts of the question. Remember that it's likely the experiment will not be an experiment you've carried out in class. That's to be expected. So you should be applying your understanding to different situations. Again, use any information given to you in the question for Physics Paper 3 to help you structure your answer. So just as a bit of a checklist, you should be describing the method used to vary the independent variable, describe how the independent variable is to be measured, describe how the dependent variable is to be measured, describe how other variables will be controlled, then describe with an aid of a clear label diagram the arrangement of the apparatus for the experiment and the procedures to be followed. So when you're considering an experimental method, think about the following things in your answer. Does the method actually test what it's being asked to? Is the method clear enough for someone else to follow? Apart from the independent and dependent variables, what is being controlled and how? Are the apparatus and techniques appropriate for what is being measured, and are they being used correctly? Will the method you are using give precise results? Are repeat measurements needed to be taken in the experiment? Is the experiment going to be conducted safely and ethically? Now traditionally, questions where students must write or evaluate an experimental method is poorly answered in AQA A-Level Physics Paper 3. So here is some feedback from the examination board indicating how students can achieve full marks on these types of questions. So students should be encouraged to describe how to change one variable and to give a suitable range of values as well as specifying how many sets of results to take. It's also expected that students will describe graphical methods of processing results, including where relevant, the significance of intercepts and gradients on graphs. To gain credit for suggested repeated measurements, students should be specific about which readings are repeated, and they must mention the averaging of those measurements. Students find it harder to describe the ways in which a suitable range of sets of results could be obtained, and few mention the advisability of taking repeated measurements of each set of the values to find means. It should be noted that general statements such as results should be repeated and averaged are not likely to attract marks in the exams. Students should be specific about which measurements should be repeated repeated. Although many students suggest that such a graph is straight when the suggested relationship is correct, few mention that it should be also going through the origin, which is something to consider. Plans seen also tend to lack detail on how independent and dependent variables can be varied and how you can record the different values. Many students don't know how to process data to obtain a straight line graph. Examiners insist on seeing that dependent variables were read, measured or recorded. These are the terms examiners expect students to use if similar questions are posed in future papers. Students can give an expression to show how their grading could be manipulated to obtain a value, but examiners are expected for the value to be the subject of this expression when it's derived. Now, no experiment is going to be perfect, and the ability to see weaknesses in the experimental setup and the techniques used is an important skill. So you should take the opportunity to think of ways to improve experiment technique, thereby reducing overall percentage uncertainties. So for any practical, consider how extra results could be taken and used. You could be considering how to measure values accurately. You should be being specific to the experiment about the error and the correction needed. We should consider how percentage uncertainties can be reduced, either by decreasing the absolute uncertainty or by increasing the measured values. And you should also consider how to control variables. So let's look at a few examples of some different experiments that are found in A-level physics. So for example, if you drop ball bearings and measure the radius of the craters produced, or the depth of the crater produced, a problem could be two results are not enough to draw a valid conclusion. So you would say take more results and plot a graph of D against D. The ruler is too wide to measure the depth of the crater, so you could use something else. So for example, an improvement could be use a knitting needle and mark the sand level on the needle and then measure with a ruler. There may be a parallax error when measuring the top level of the crater, so keep your eye parallel to the horizontal level of the sand or use a stiff card to measure as a marking point to stand perpendicular. It's difficult to release the ball bearing without giving it a sideways velocity, leading to a distorted crater, so you could use an electromagnet to release the ball, or the crater lip is of varying height, so you could always say to measure the highest point. Another experiment is to measure an object under free fall. So a problem could be two readings for just two masses were not enough. So you could use a greater range of different masses and plot a graph of average time to fall to the ground against the mass of the object. You could say it was difficult to start the stopwatch at the same instant that you dropped the stone and to stop it exactly as it hit the ground. So you might have been late because of the reaction time. So you could film the fall of each stone with the video camera, which has a timer in the background. When the video is played frame by frame, see the time which the ball hits the ground on the timer. Your hand was not steady, so I may have dropped the stone from not exactly the same height each time. So you could use iron objects which hang off from an electromagnet. When the current in the electromagnet is switched off, the object falls. The heavier stone was larger in size, and it was important that the bottom of each stone start at the same height. There may have been a parallax error. So you could clamp a meter ruler vertically and start the bottom of each stone at exactly the top of the ruler each time. To avoid parallax error, make sure the line of sight is horizontal at right angles to the rule. The times that I measured were very short, not much greater than my reaction time, so the reaction time had a greater effect. So you could increase the distance of the fall so that the times are larger. This will make the uncertainty in each measurement smaller in proportion to the time being measured. If you consider oscillations, taking readings for two lengths was not enough. So use more than two lengths and plot a graph of average time squared against the length of the string. It was difficult to judge the end of the swing, so you could use a fiducial marker at the center of the oscillations as the position to start and stop a stopwatch. Use an electronic timer placed at the center of the oscillation to measure the time, or you can make a video of the oscillation with the time in the background and play it back frame by frame. The oscillations died away too quickly. Use a heavier mass which swings longer. The times were too small to measure accurately, as my reaction time was a significant fraction of the total time, so you could use a longer string, or time 20 rather than 10 oscillations. Or it could be difficult to measure the length to the center of gravity of the weight accurately, so use a longer string so the error has less of a proportion to the value. Measure the length to the top of the weight and use a micrometer to measure the diameter of the bob and add on half the diameter to the length of the string. You could think of a forces experiment that taking readings for two masses was not enough, so you could use more than two masses, and plot a graph of force against mass. It was difficult to zero the Newton meter used horizontally, so you could use a force sensor in a computer, or you could use a pulley and string to connect a tray to the block, then tip sand onto a tray until the block starts to move. The weight of the sand in the tray is then the force. The reading of F was very low on the scale and gave a large percentage uncertainty, so you could use heavier masses on top of the block. The block starts to move suddenly and it's difficult to take the readings as this happens, so you could video the experiment and play back frame by frame to see the largest force or use a force sensor and computer. Different parts of the board are rougher than others, so mark round the board with a pencil at the start and put it back to the same place each time. Or you could think of a resistivity experiment. So taking readings for 2 lengths were not enough, so use more than 2 lengths and plot a graph of the voltmeter reading against length. It's difficult to measure the length of a wire as the clips have width and you don't know where inside they grip the wire, so you could use narrower clips or solder the contacts onto the wire. The scale is not sensitive enough and it only can measure to 0.05 volts, so use a voltmeter that reads to 0.01 volts, so use a digital voltmeter. The values of the voltage are small, particularly at 0.30 meters, so you could use a larger current so that when the L equals 0.50 meters, the voltmeter readings at the top of the scale. The voltmeter reading fluctuates because of contact resistance, so you could clean the wires with wire wool first, or other factors may have changed the resistance. For example, the temperature may have increased because of the current. Wait a long time until the wires reach a constant temperature, or use a smaller currents but with a more sensitive voltmeter. So there's some examples of how you could improve experimental methods. Now, when analysing or evaluating experimental results given to you in an investigation, you need to consider the following. What patterns are shown in the experimental data? Was the experimental data valid and precise? How accurate is the experimental value measured? Is the resolution of the measuring instrument high enough? Is there any anomalous results? If so, what caused this? How large is the percentage uncertainty? How large is the percentage difference? Now, it's important to note that for any conclusion, it can only be valid over the experimental data that it's gathered for. Trends can be extrapolated past the data set, but this doesn't mean it will continue, as there's no evidence to suggest that the relationship will continue in the same fashion. Now again, when you evaluate your experimental method and your experimental write-up, you've always got to consider, have all variables been controlled or monitored? If not, how could they be controlled or monitored? What has caused any systematic or random error in the investigation? And how could the percentage and absolute uncertainty be reduced? So let's now have a look at the concept of errors. So a true value is the value that would be obtained in an ideal measurement. Now, a measurement error is the difference between a measured value and the true value for the quantity being measured. Now, there are 2 main types of errors in investigations: systematic errors and random errors. Systematic errors are errors which cause the same uncertainty on the experimental results, and random errors are errors which cause different uncertainties on the experimental results. Systematic errors will affect the accuracy of results, while random errors will affect the accuracy and the precision of results. Now, both of these errors will affect the absolute uncertainty of the experimental values. To reduce the percentage uncertainty in an experiment, you must use larger values for the experimental results, or you must use a measuring device with a greater resolution, as this will lower your absolute uncertainty. Now, an example of a systematic error is a zero error, and an example of a random error can be a parallax error. Now, the impact of a systematic error is that it changes the intercepts of the graph, not the gradient though, but the impact of a random error is it changes both the intercepts and the gradients of a graph, so it makes the line of best fit difficult to plot. Now, you can reduce systematic errors by changing your experimental technique, so resetting the voltmeter, ensuring the balance is flat, but you can only reduce random errors by carrying out repeats until concordant results are achieved, you've removed anomalies, and you've calculated a mean value. Now, for your systematic error, you should compare the results with the expected value and subtract the error from this. So an example of a systematic error might be that a spring on a force meter might over time become weaker so that the force meter reads consistently high, or that the magnet in an ammeter might over years become weaker and the needle might not move as far around the scale as expected. Now, you could have a parallax error as a random error or as a systematic error if you're always looking at it from the same angle and not directly from above when taking a measurement. Now, reasons for systematic errors could be the way in which measurements are taken or faulty measuring devices. The reasons for random errors are that factors are not controlled in the experiment and there's difficulty in deciding on the reading given by a measuring value. Now, repeating and averaging results will only reduce random errors when anomalies are removed from results. Systematic errors tend to be discovered when certain results are taken in investigations and compared to standard values. Now you can remove systematic errors by calibrating your equipment. Now you measure a known value, and if there's a difference between the measured and the known value, this should be used to correct the error, and this is called calibration. Now, systematic and random errors produce absolute uncertainty in the investigation along with the resolution of the measuring device. Reducing systematic and random errors will reduce the absolute uncertainty in your investigation. Now, good equipment and good technique will reduce the uncertainties introduced, but difficulties in judgments in making observations will always limit the precision of your measurements. Now, it's important you ensure that phrases such as accurate and precise are used correctly in your experimental write-up. Accuracy is how close the measurement result is to the true value. The closer the measurement result is, the more accurate it is. Precision is how close repeated measurements are to each other. The closer repeated measurements are to each other, the more precise the measurement is. And the image below can show you the difference between accurate and precise, because results can be not accurate or precise. They can be accurate but not precise. They can be not accurate and precise, or they can be both accurate and precise. Now, some readings don't vary widely, but are still not precise because they're measured with a device with a low resolution. So you've always got to remember that. Now, the resolution of a measuring device is the smallest increment in the measured quantity that can be shown on the device. Now, precision can be improved by carrying out more repeated measurements and removing anomalous results from the dataset. Accuracy and precision can be improved by carrying out bigger measurements. So, for example, measuring 10 oscillations as opposed to 1 oscillation. Now, valid results in an experiment arise from a suitable procedure being followed to ensure that you answer the question the investigation is asking. Another two phrases which shouldn't be confused are repeatable and reproducible. Results are repeatable if you can repeat an experiment multiple times and get the same results. But results are repeatable if another team of experimenters can recreate your experiment using different equipments or methods and get the same experimental results. So let's now have a look at the idea of measurement techniques. Now you need to familiarize yourself with the use of simple measuring instruments such as meter rules, balancers, protractors, stopwatches, ammeters and voltmeters, and even more complicated ones such as micrometer, screw gauges and calipers. Now, when using measuring instruments like this, you need to ensure you're fully aware of what each division on a scale represents. If you look below, you'll see on the first ruler, each division is 1 mm, and on the second, each division is 2 mm. So you've got to be aware of the scale of the measuring device. Now, if you use instruments incorrectly, you may introduce errors into your readings. For example, when you take a reading, your line of sight should always be perpendicular to the scale you are using. Otherwise, you introduce a parallax error. Now, to set an object vertically, you can use a set square perpendicular to the object in the bench, or you could use a plumb line and place it next to the object. If it's observed at a perpendicular angle to be parallel to the object is vertical. Now, you can set an object horizontally by using a set square to align it perpendicular to a vertical ruler. Now, a micrometer screw gauge, or more simply a micrometer, is shown below. This has two scales. The main scale is on the shaft and the fractional scale is on the rotating barrel. Now, one rotation of the barrel moves the end of the barrel 0.50 mm along the shaft. Now, the barrel has 50 divisions, so each division you can see represents 0.01 mm. So as we said, the micrometer is made of two scales. The main scale, which is on the sleeve or the barrel, and the thimble scale, which is the rotating scale on the thimble. Now, the spindle and anvil are clamped around the object being measured by rotating the ratchet. This should be tight enough that the object does not fall out, but not so tight that it's deformed. Never tighten the spindle using the barrel, but only the ratchet, as it will reduce the chances of over-tightening and gaining a zero error. So you can take a reading from the screw gauge micrometer with the following method. You read the main scale first, and each division represents 0.5 mm. Now, there are 5 divisions on this particular main scale, so to the nearest 0.5 mm, it's 2.5 mm. You would next then read the thimble scale. Each division on here represents 0.01 mm. So you read the number that aligns with the main scale and multiply by 0.01. So here it's aligned with 17. So it's 17 times by 0.01 or 0.17 mm. You add the two values, one from the main scale, one from the thimble together to get the final measurement. So here it's 2.5 plus 0.17, 2.67 millimeters. Now to use the micrometer, remember to turn the barrel until the jaws just tighten on the object. Some micrometers have a ratchet or slip mechanism to prevent the user from tightening too hard and damaging either the micrometer or the object. Now before you start using micrometer or calipers, it's usual to check if there's a zero error. This is done by bringing the jaws together without any object between them. Obviously then the reading should be zero, but if the instrument is worn or has been used badly, the reading may not be zero. When you have taken the zero error reading, it should be added or subtracted to every other reading that you take with the instrument. If the jaws do not quite close to the zero mark, it's a positive zero error, and therefore this zero error should be subtracted. Now vernier calipers are another distance measuring tool that uses a sliding vernier scale. So this can also be used to measure diameters and thicknesses just like the micrometer. However, you can also measure the length of small objects such as a screw or the depth of a hole. Now calipers are designed to grip an object with two jaws and to measure the diameter of the object. They can also be used to measure the internal diameter of a tube. For example, if the two prongs are placed just inside the tube and the moving part of the calipers is adjusted until the prongs just grip the inside of the tube. Now in this instance, the two upper or lower jaws are clamped around the object and the sliding vernier scale will follow this and can be held in place using the lock and screw. You can then take a reading from the vernier scale. So we'll talk about the vernier scale in a bit more detail, but you read off the centimetre mark to the left of the vernier scale. So here it is 1 centimetre. You then read off the millimetre mark to the left of the vernier scale. Here again it's 3 millimetres. You find the point where the line matches up with the line on the bar scale. This tells you the tenth of a millimetre, so it's 0.3 millimetres. You would add all three values to get 13.3 millimetres. Now in this image, the calipers shown here are dial calipers. So although other versions such as vernier calipers can still also be used, you can also use dial calipers as well. As the sliding scale moves along, one rotation of the dial moves the jaw 1 millimetre further apart. Since the dial is shown 100 divisions, each of these divisions is 1 over 100 or 0.01 millimetres. So the object shown has a diameter of 12 millimeters on the fixed scale and 25 or 0.25 millimeters on the dial. So you can add them together, so the overall diameter is 12.25 millimeters. Now in general, micrometers have a smaller measuring range than a vernier caliper. However, the micrometer has a better accuracy due to having a better resolution. Now the vernier caliper is quicker to use, whilst the micrometer involves rotating the thimble. Now in general, the micrometer can therefore be linked into this, because we can say that to take many measurements, a caliper will be easier to use. Now, vernier calipers are an example of a device which uses the vernier scale, as discussed before. Now, the vernier scale typically enables length measurements to be made to an extra significant figure that otherwise would not have been possible. Now, a regular ruler, for example, can measure to the nearest millimetre. If you add a vernier scale onto the ruler, the same ruler can now read to the nearest tenth of a millimetre. So the distance in whole millimeters is always rounded down is given by identifying the mark on the main scale which lines up or is past the 0th mark on the vernier scale. So for example here, you know that the reading is between 4 and 5, as the vernier scale on the picture, which is the upper scale, it starts after 4 yet before 5 on the main scale, the lower scale. Now the number of vernier scale divisions, the upper one, before it lines up with the main scale division, the lower one, tells you the next significant figure. As you can see on this diagram, here the 5th vernier scale division lines up with the main scale. Remember, the first line, the longest one, which is just after 4, counts as 0. So you go 0, 1, 2, 3, 4, 5. The 5th one is therefore the one that lines up with the main scale. So the answer is therefore 4.5. Now when the measurement is the exact number on the main scale, the 0th and the 10th division is shown on the vernier scale lines up with the marks on the main scale. Now you can also measure quantities in experiments by using either analog or digital meters. Now analog meters display values on a dial, usually either with a needle or a moving pointer. Now analog meters are useful as it's easy to see a change on these devices and you can change the scale easily. Analog meters though, however, can cause experimental errors as they're susceptible to parallax errors when taking measurements. Now analog meters should be viewed with the observer directly in front of the pointer when the reading is being made. Now this can be achieved by using a plane mirror. So a plane mirror is placed behind the pointer, and the image of the pointer must be directly behind the pointer to ensure that the observer views the scale directly face on. Now, analog meters will display values on a dial, usually with a needle and a moving pointer. Now, therefore, all analog meters will have a full scale deflection and an interval. So the full scale deflection is the full range of the meter. So in this example, the full scale deflection is 500 volts. Now in investigations, you must ensure that the full scale deflection on your analog meter must be large enough to record all results in your investigation. Now the interval on your analog meter is the difference between each point on the scale of the meter. So in this example, the interval is 10 volts. Again, in investigations, the interval must be small enough to gain a different reading on the scale for each measurement. In investigations, there tends to be a compromise between the full scale deflection and the interval values for the meter. If the interval values are too large, then not all of the results can be measured by the measuring device. If the full scale deflection or the range of the device is too large, then the measuring device is not sensitive enough to accurately record the results. Let's now have a look at the concept of uncertainties. Now in our results, you must always write down a numerical value of error in the experimental value. The error gives a range of values the measurement must lie in. So for example, if it's 2.5 plus or minus 0.1 volts, the reading could be 2.4 volts or 2.6 volts. So it means you're very confident that the result relies within these two values. So if we consider the measured value, say for example to be 10 volts, and it's plus or minus 2 volts, well then the actual value is in the range of 8 volts to 12 volts. Now values should always be presented in the following format. Now the range of possible values considers the mistakes made in the experimental technique and the resolution of the measuring device used. So here we call this the absolute uncertainty. So a combination of measuring device error and experimenter error. You could also write it as a percentage uncertainty, where you write the uncertainty as a percentage of the experimental value. So for example, plus or minus 20%. So each measurement has some inherent uncertainty. The important question is to ask whether an experimenter can be confident that the true value lies in the range that's predicted by the uncertainty that is quoted. So good experimental design will attempt to reduce the uncertainty in the outcome of an experiment. The experimenter will design experiments and procedures that will produce the least uncertainty to provide a realistic uncertainty for the outcome. Now, in assessing the uncertainty, there's a number of issues that have to be considered. These include the resolution of the instrument used, the manufacturer's tolerance on instruments, the judgments that are made by the experimenter, the procedures that are adopted, for example repeated readings, and the size of increments available. Now, a combination of the above factors means that there can be no hard and fast rules about the actual uncertainty in measurements. There are 4 ways we believe to calculate the absolute uncertainty in a value. Method 1, calculating uncertainty due to the measuring device used. Method 2, calculating uncertainty due to experimental technique. Method 3, calculating uncertainty due to a stated value given. And method 4, calculating uncertainty due to the variation in readings. Now we can assess from an instrument's resolution the minimum possible uncertainty. Now only the experimenter can assess the other factors based on the arrangement and the use of the apparatus, and a rigorous experimenter would draw attention to these factors and take them into account. Now once the absolute uncertainty has been calculated, we can then work out the percentage uncertainty. Now it tends to be that when questions use the term uncertainty, they're referring to the absolute uncertainty. I would only calculate percentage uncertainty when the question explicitly states it. Now absolute uncertainty can only be reduced by improving your experimental technique or by carrying out repeats of your results. So let's have a look at reviewing the first method for calculating absolute uncertainty. So you should know that there are actually 2 types of value which can be taken by a measuring device. The first one is readings. These are values found from a single judgment when using a piece of equipment. So this means looking at a device once to take a reading. So it implies that, for example, one judgment equals a reading. So for an example, when measuring the mass of a beaker with a balance, you only look at the balance once, whilst measurements are values taken as the difference between judgments of two values. So you're looking at two times to take a measurement. So for example, when measuring the length of a wire with a ruler, you're looking at it twice. So this makes it a measurement. So two judgments make it a measurement. So readings could be things like using a thermometer, a top pan balance, a measuring cylinder, a digital voltmeter, a Geiger counter, a pressure gauge, whilst a measurement could be using a ruler, a vernier caliper, a micrometer, a protractor, a stopwatch, an analog meter. Now, the uncertainty in a reading when using a particular instrument is plus or minus half of the smallest division. So, for example, a temperature measured with a thermometer is likely to have an uncertainty of plus or minus 0.5 degrees Celsius if the graduations are 1 degree apart. That's because you're only taking one value from the device. So, for example, the value could be read as 30 degrees. However, for this scale, you would say it's 30 if the reading was between 29.5 and 30.5, because you'd round it to 30. So this means the answer is 30 plus or minus 0.5 degrees. So it tells you that you can't have the uncertainty more or less than sensitive than the answer stated. So you would therefore think that the confidence is consistent. So it's really important you keep that consistency when you're taking your judgment. Now, it gets a bit more challenging when you're taking a measurement, because when you're taking a measurement, you're taking two judgments, so two uncertainties must be included. Now, as both judgments have an uncertainty of half of a scale division, therefore the overall uncertainty of the measurement, because there's two of them, means you've got to add them together, so it's in fact the uncertainty of one division. So the uncertainty for a measurement is in fact the same as the scale division. So for example, a temperature change is measured with a thermometer is likely to have an uncertainty of plus or minus 1 degree Celsius if the graduations are 1 degree apart, because each of them has an uncertainty of plus or minus half a division, so added together it is in fact one division. So we can summarize the rules for absolute uncertainties with the following statements. The uncertainty of a reading, which is one judgment, is half of the smallest scale reading, whilst the uncertainty of a measurement, which is two judgments, is plus or minus 1 of the smallest scale reading. Let's now have a look at how you can calculate the uncertainty due to experimental technique. So there are some instances where you've got to include uncertainty due to human experimenters. This is added on to the measuring device uncertainty we just calculated. So for example, a stopwatch might have a resolution of plus or minus 0.01 seconds due to the measuring device, but the uncertainty in the measurement is much likely to be higher due to the reaction time of the experimenter. So you've got to add this onto the absolute uncertainty of the measuring device to give a larger uncertainty value. So if you think the experimenter causes more uncertainty by carrying out the measurement than the device produces, you've got to state this uncertainty and not the measuring device uncertainty. So another example would be if a student measures the length of a piece of wire, it's very difficult to hold the wire completely straight against the ruler. So the uncertainty in the measurement is likely to be higher than the plus or minus 1 millimeter uncertainty of the ruler. Depending on the kinks of the wire, the uncertainty could be plus or minus 2 or 3 millimeters. Now when you're finding a value for this uncertainty, you must estimate this value. There is no right answer for estimating this particular value. Now, another example could be the uncertainty of the reading from digital voltmeters or ammeters depends on the electronics and is strictly not the last figure in the readout, as the value can fluctuate greatly. Or when timing a pendulum swing or a spring oscillating, the stopwatch might have a resolution of plus or minus 0.1 seconds. However, the human reaction time to carry this timing out is much larger than the resolution. It could be plus or minus half a second. Now, as we said before, with this method, when finding a value for this uncertainty, you must estimate the value. There is no right answer for estimating this value. Now, the third method of calculating uncertainty is the uncertainty due to a stated value given. If you were given a value from a datasheet or in a question, you must still consider its uncertainty. In these situations, you assume the uncertainty to be plus or minus 1 of the last significant digit. So the value of charge on electrons given on the datasheet is 1.60 times 10 to the minus 19 coulombs. So in this case, the uncertainty is plus or minus 0.01 times 10 to the minus 19 coulombs. Now the uncertainty may be lower than this, but without you knowing the details of the experiment and the procedure that led to this value, there's no evidence evidence to assume otherwise. So this allows you to consider the uncertainty in every value in the investigation. So an example of this would be the following. If the number of lines per meter is quoted as 3.5 times 10 to the 3, it's usual to assume that the uncertainty is plus or minus 1 in the last significant figure. So it would be plus or minus 0.1 times 10 to the 3, since there's no indication of the uncertainties in the measurements from which the value came. So it would be 3.5 plus or minus 0.1 times 10 to the 3 per meter. We'll now review the final method to calculate absolute uncertainty. Now that's if you have to calculate uncertainty due to a variation in readings. Now if you have repeated values and then derive a mean, the absolute uncertainty can be calculated from the variation in the repeated readings. Now this comes from the idea that the maximum possible value for the result is the largest value of the repeated readings, and the minimum possible value for the result is the smallest value of the minimum readings. Now when looking at the variation in the readings, you must first remove any anomalous results in your data set. So in this particular example, you find the highest value, which is 1.32, you find the lowest value, which is 1.22. So this means that the value lies in the middle of these two numbers, these limits. So the uncertainty must extend to the highest value and the lowest value. So therefore we can find the uncertainty by getting the range and dividing it by 2. So the range here is 0.10, we divide it by 2 and we get 0.05. So our mean distance is the average value, 1.23, plus or minus 0.05. So as we said before, this happens because you're confident that the value lies between the highest value recorded and the lowest value recorded. Now in an investigation where repeats are taken, it must lie within this range. So we can assume that the answer is the middle point between the highest value and the lowest value. So we can therefore state that the absolute uncertainty is half of the range, and it allows the full range to be represented when we use the plus or minus symbol. So as we said before, if you find half of the range, this method will actually reduce absolute uncertainty, because repeating results until you gain concordance means that the anomalous results can be discarded, so you would leave a smaller range of data to take your absolute uncertainty from. So like we said before, in this particular example, we are confident that the answer lies between 2 meters as the highest possible value and 1.80 meters as its lowest value. So we can therefore state the value as 1.90 plus or minus 0.1 meters. So we can actually take all these ways of calculating absolute uncertainty and then work out the percentage uncertainty. So the percentage uncertainty in a measurement can be calculated using the equation that the percentage uncertainty is the absolute uncertainty divided by the value times by 100. Now if you have a repeated measurement, the percentage uncertainty is the absolute uncertainty divided by the mean value times by 100. Now the absolute uncertainty for repeated measurement can be worked out from our previous method. Now it's good practice to reduce the percentage uncertainty to the lowest value possible. This is done by using the largest measurement values in your investigation, or by using a measuring device with the smallest resolution available. So as you can see here in this example, the percentage uncertainty in this case would be the absolute uncertainty, which is 0.1, divided by the value, which is 10, times by 100 is therefore going to be equal to 1%. So we can therefore say it's plus or minus 1%. Now when you state your percentage uncertainty, a unit is not required, but the percentage uncertainty should be given to the same number of significant figures as the value, like in the example above. Now when we deal with formulae and equations in physics, we have uncertainty from different values. So we must combine these uncertainties to find the overall uncertainty. So this is the overall uncertainty of a calculated value based on the uncertainties in the values needed to calculate it. So for example, if we say that power equals potential difference times by current, the uncertainty in the power is a combination of the uncertainty in the potential difference and the uncertainty in the current. So let's look at the rules which allows us to combine uncertainties. So if, for example, we are adding or subtracting a value in an equation, so for example, extension equals stretch length minus original length, that if the quantities in the equation are either added or subtracted, you must add the absolute uncertainties. Now, if you have multiplication or division in an equation, for example, resistance is potential difference over current, in both instances, if quantities are either multiplied or divided, you must add the percentage uncertainties together. And if you have powers in your equation, so for example, area equals pi r squared, well then to find the overall value, you must multiply the percentage uncertainty by the power. So it's very, very important you carry this out. So let's just have a look at this key information. So there are 4 ways to calculate the absolute uncertainty in a value. Method 1 is to calculate the uncertainty due to the measuring device used. This is the resolution of the device if it's a measurement, but it's half the resolution of the device if it's a reading. The second method is to calculate the uncertainty due to experimental technique, which is an estimation. You can calculate the uncertainty due to the stated value given, and this is plus or minus 1 of the last significant figure in the value. And then finally, the fourth way is to calculate the uncertainty due to the variations in the reading, which is the range of the repeated values divided by 2. We know that uncertainties is a measure of how sure you are of a value. It's the range of values that your result must lie in. The absolute uncertainty expressed as a value is the value times by the percentage uncertainty over 100. The percentage uncertainty is the uncertainty expressed as a percentage of the value. So that is absolute uncertainty divided by value times by 100. And if it just says the term uncertainty in a question, it refers to the absolute uncertainty. We can combine uncertainties when we have more than one uncertainty in an equation. If you have to add or subtract values in your equation, you must add the absolute uncertainties. If you multiply or divide values in your equation, you must add the percentage uncertainties. And if you're using powers in your equation, you must multiply the percentage uncertainty by the power. Now remember, you always add uncertainties, you'll never subtract them. So remember, when you add or subtract, you will add absolute uncertainties. And if you multiply or divide, you will add percentage uncertainties. Let's now have a look at relationships of data. Now we can mathematically prove that relationships are either directly or inversely proportional from a data set. Now directly proportional means that the values increase or decrease in the same proportion as each other, whilst inverse proportional means that one value increases, the other value decreases in the same proportion. You can observe direct proportionality as a straight line through the origin, and you can observe inverse proportionality as a curving line downwards in your graph. So this tells us mathematically, in direct proportionality, y equals kx, where k is a constant, so therefore it equals y over x, whilst in inverse proportionality, y is equal to k over x, where again k is a constant, so the constant is y times x. So this tells us a couple of things. If the terms in the data set are divided, the y and the x values are divided by each other, if they are directly proportional, they should give the same value of constant each time, whilst if the terms in the data set are multiplied, the y and the x term, well they should give the same value of constant if it's inversely proportional. So let's have a look at this idea of direct proportionality. So you can see in this data set, if the terms are divided, so a divided by f in this particular example, or that tells us this should give the same value of constant, which it does, the k is the same value. So this proves mathematically that the two factors are directly proportional to each other. Now in this instance, if the terms in the data set are multiplied by each other, it should give the same value. So when a and b are multiplied by each other, they give the same value of constant, and they do. It's 24 each time. It tells us that the two values are inversely proportional to each other. Let's now have a look at graphs. So many, but not all graphs you meet will be straight lines. So the points may not all lie exactly on the straight line, but it is your job in your exam to choose the best line. So generally there should be equal points on either side of the line, but not 3 on one side of one end and 3 on the other at the other end. And sometimes all the points bar 1 will lie on the line. So as you can see in this following image, the line on the first graph is too shallow. By swinging it around so that it's a bit steeper and it gets closer to more points and they're more evenly distributed above and below the line, such as on the right hand side, that's a better line for your graph. Now when you've drawn your line of best fit in, you can then find the gradient of your line of best fit, and you should always do this by showing you're working out by drawing a triangle on the line. Now you'll see here that the line of best fit forms a hypotenuse. Now the hypotenuse of this triangle should be at least half as big as the overall line of best fit. You should always draw your gradient triangle on the graph and show you're working out. So as you can see here, we've got a large gradient triangle on the graph. It's very clear, it's very obvious, and it's at least least 50% of the line of best fit. If you don't show your gradient triangle on the graph, then you'll not receive any marks for this skill. Now, the larger the gradient triangle, the more the reliable the results, as more values are considered in your dataset. Now, in this instance, this gradient triangle can only be produced on a straight line section of a graph. Now, when drawing curves, you'll need to draw a single smooth curve without any jerks or any feathering, as with a straight line, not every point will lie precisely on the curve, and there should be a balance of points on either side. Now, as you can see in the following example, in the first graph, the student has joined each of the points used in a series of straight lines. This should never be done in your graph for data analysis. The second line is much better, although there's some feathering on the left hand side. It's a bit sketched, so you can see multiple lines. Now you can see in the third graph it's a well drawn smooth curve which goes through the majority of the points, and there's an even number of points on either side. Now, if you do draw a curved line for your line of best fit, there's a further method of working out the gradient. Now, if the line of best fit is a curve, you must draw a tangent to the curve at the point at which the gradient is wanted. You must then find the gradient of the tangent. Once again, this is done by drawing in a gradient triangle onto your graph, and remember, this only allows you to find the gradient of this one instantaneous point. So this is rather a measure of instantaneous rate of change, which will be important if you consider what data you want to work out. Now, whether it is a gradient or whether it is a straight line, you can use this to determine the overall gradient. Now, the gradient is the change in y over the change in x. Now, in an investigation, you should always show your working out and the units of this value. You should not just write down the gradient. Now, we can use the gradient and the y-intercept to determine the equation of the line. So it's very important that you should be able to translate graphical data into the equation of a straight line, which is y equals mx plus c, where y is the y-axis value, m is the gradient, x is the x-axis value, and c is the y-intercept. So as you can see in this particular example, we have y and we have x. We've worked out a gradient with our gradient triangle to be 0.24. We've worked out our y-intercept to be 7, and this allows us to work out different values if you had a value of y or x. Alternatively, if you had a gradient and you had a value of y and x, you could then work out your y-intercept. Now, again, you can see here, you can calculate values which link into different parts of the graph to work out key things. So in this particular experimental investigation, displacement is on the y-axis, time is on the x-axis. In this instance, the gradient is 4.85 and c is 0.20. So we can rewrite this as an equation, which is displacement is equal to 4.85 times by time plus 0.20. Now, in questions, you'll be expected to calculate values from gradients and y-intercepts. Now, you can work out what the gradient represents on the graph by considering the equation. Now, remember, the equation of a line is y-axis equals gradient times by x-axis. So in this example, if we say force equals spring constant times by extension, well then the force is on the y-axis, the extension is on the x-axis, so therefore the gradient must be the spring constant. In this example, force is equal to mass times acceleration, but we know y equals mx. So the force is the y-axis, the mass is the x-axis, and the gradient is the acceleration. Now, it doesn't have to just be single terms. You can have powers in there. So, for example, if the physics equation is t squared equals 4 pi squared over k times by m, well, y equals mx plus c. So time squared is on the y-axis, mass is on the x-axis, and gradient is equal to 4 pi squared over spring constant. You can also consider it if you have the y-intercept as well. So as we in this example, just pick a random equation that links into nothing. We could say that phi is equal to rho theta plus epsilon. So what we can therefore say is y equals mx plus c. So we can say y, therefore, if phi is y and rho is x, well, gradient will be theta, and therefore it means that the epsilon will be y. So it's very important that if you are given an equation, you've got to rearrange it into a form where the y-axis term is by itself, and then you can work out values, because the term multiplied by the x-axis will be the gradient, and the term being added to the term being added to the x-axis term is the y-intercept. So you don't have to know what the equation was beforehand, as long as you stated that and you rearranged it correctly. Now, if you have y, m, and c in the equation, we can then use that to find the y-intercept. Because to find the x-intercept, because to find the x-intercept, you would set the y value to 0 and then work out the value for x in the equation, and vice versa for the y-intercept as well. Now, the area under the line can also give useful information. Now, the area links the y-axis quantity and the x-axis quantity. So, for example, if the shape is a triangle, we can say that area is equal to a half times by y quantity times by x quantity. If the shape is a square or a rectangle, we can say that the area is the y quantity times by the x quantity. And if the shape formed by the line of best fit is an irregular shape, well then the area is equal to the y quantity times by the x quantity times by the number of squares that you've counted underneath your curve. Now, examples of graphs with useful areas include a velocity time graph, because the area would therefore be velocity times time, which is displacement. An acceleration time graph, because the area is the acceleration times the time, which is the change in velocity. A power time graph. Now, area is power times time, which is the work done. Or a PD charge graph. Now, the area is going to be PD times charge, which again is the work done. Now, to show uncertainty in your experimental values, you should always draw error bar on your plots on your graphs. Now, error bars are a graphical representation of the variability of data and are used on graphs to indicate the error or the absolute uncertainty in a measurement, so they give a general idea of how precise a measurement is. Fundamentally, error bars are the graphical representation of uncertainty that you've previously calculated, so they are a graphical interpretation of the absolute uncertainty in a value. Now, the error bars represent the absolute uncertainty as we previously mentioned. Now, really they should be drawn on all x-axis and y-axis values in A-level physics. Now, in your error bar, you can see here that the error bars will show the highest possible y and x value and the lowest possible y and x value. So again, these values are calculated from the absolute uncertainties you've worked out previously. So the error bars are an interpretation of the range of results you are sure that your answer lies in. So the error bars can be used to determine if any results are anomalous in an investigation. So a result is anomalous if the line of best fit does not pass through any of the error bar of that value. So you can see here that the result at the bottom does not have any of the line of best fit go through the error bars, so we would determine it is anomalous. We can also use error bars to determine the percentage uncertainty of a value. Now, this is a method which is different to the one we've previously looked at. So what you can do with your data, with your error bars, is you can use the best and worst lines of best fit from the error bars to determine the values. So to find the uncertainty in a gradient, two lines should be drawn on the graph. One should be the best line of best fit, which is the normal line of best fit drawn. The second line should be either the steepest or shallowest gradient of line of best fit possible from the data. The gradient of each line should then be found. Then the percentage uncertainty is the difference in the best line of best fit and the worst line of best fit gradients, and then we divide it by the gradient of the best line of best fit and we times it by 100. Now, this gives a result like absolute uncertainty worked out mathematically. This in theory is like the process of halving the range of the results to find the absolute uncertainty. So it's the same equation as the one used to work out absolute uncertainty mathematically. So absolute uncertainty via this method is the difference between the best and the worst gradients, or the difference between the two worst gradients, the steepest and the shallowest line, divided by 2. Now, the absolute uncertainty can also be derived via the y-intercept as well, because it can be found with the y-intercepts as well as the gradients. So we can say our absolute uncertainty is the difference between the best and the worst y-intercepts of the two lines, or the difference between the two y-intercepts, which are the steepest and the shallowest lines, divided by 2, or we could work out the percentage uncertainty as the difference between the best and the worst y-intercept divided by the best y-intercept times by 100. Now, this methodology can also be used for log graphs. Now, when a log graph is used, we need to include error bars, and we must find that the logarithm of the measured value and the logarithm of either the largest or smallest likely value. The uncertainty in the logarithm will therefore be the difference between the two. Now, as you can see here, in this information we have the graph with a line of best fit and a graph with a line of best fit and worst acceptable fit. So in this left hand side one, the gradient is going to be change in y over change in x, which is 1.6. Then the gradient of the worst acceptable fit line is 1.4. So at that point the absolute uncertainty is the difference between the two, which is 0.2. If we then wanted to find the percentage uncertainty, it would be 0.2 divided by the gradient of the line of best fit, which is 1.6. So 0.6 over 1.2 times by 100. Let's now have a look at the idea of logarithms. Now the logarithm of a number is the exponent to which the base must be raised to produce that number. So for example, how many 3's do we multiply to get to 81? Well, 3 times by 3 times by 3 times by 3, or 3 to the power 4 equals 81. So the logarithm to the base 3 of 81 is 4. So we would write the number of 3's you need to multiply to get to 81 is 4. So therefore log to the base 3 81 equals 4. So these two things are equivalent, as we can see in this particular graphic here. Now we write the logarithm to the base 10 as log 10 or just log. So log 10 of 10 is 1. So we say log 10 1. Log 10 of 100 is 2. So log 100 is 2. Log 10 of 1000 is 3, or log 1000 is 3. Log 10 of 10,000 is 4, or log 10,000 equals 4. It's a good way of expressing orders of magnitude in physics. So we use logarithms when we consider data across many orders of magnitude. Now there's a special case for logarithms, which is the irrational number e, which is 2.7188281 as the base. Now when using this base, log e, we call this the natural logarithm, and we use the shortened notation of ln. Now there are a series of rules which are true for all logarithms, both natural logs and base 10 logs, and that is that log AB is equal to log A plus log B, or natural log AB is ln A plus ln B. Log kx is log k plus log x, or natural log kx is natural log k plus natural log x. Log a over b is log a minus log b, or natural log a over b is ln a minus ln b. Log d over t is log d minus log t, or natural log d over t is ln d minus ln t. In log x to the power of n is equal to n log x, or natural log x to the power of n is n log x. So therefore log c to the power of z is z log c, or natural log cz is c ln c. Now you're not given these rules in your examination, you've got to be able to memorize them and apply them to different situations. So we to use logarithms to work out values in exponential equations found in physics. So for example, the charge on a capacitor. So the decay of charge on a discharging capacitor is proportional to the amount of charge left on the capacitor, which we know from previous work is Q equals Q0 e to the power minus t over RC. So we can use logarithms to find values in this equation, as it uses an exponential term. Because it's using that e term, we've got to use the natural logarithms. So the question might ask you to rearrange the equation to find resistance R of the circuit. So the first step is to rearrange the equation to have the exponential term by itself. So it becomes Q over Q0 equals e to the power minus t over RC. We take natural logs of both sides because it's exponential term there. So natural log Q over Q0 equals natural log e to the power minus t over RC. This simplifies on the right hand side, as natural log e will just turn into the power term by itself. So natural log Q over Q0 equals minus t over RC. As shown in our definition of a natural logarithm, when you naturally log an exponential term, the exponential term becomes a standard part of the equation, and then finally we rearrange the equation to make the wanted term the subject of the equation. So here R equals minus t over natural log Q over Q0 times by C. Now you can also plot exponential relations using the natural log. So let's consider the equation y equals ke to the power minus ax. You should remember to take the natural logs of both sides because there's an exponential term. So log y equals log k e to the power minus ax. We can then use a previous logarithm rule and separate out the two multiplications to say log y equals log k plus log e to the minus ax. We can then use the definition of the natural logarithm to simplify this further and remove the exponential term and bring the power term to be a natural term in the equation. So natural log y equals natural log k minus ax. This is like a y equals mx plus c equation. So that means we'll get a straight line equation, and that means y is natural log y, c minus c is going to be log k or natural log k, m is going to be a, and x is going to be x. So we will get the following graph. So if we plotted natural log y on the y and x on the x, we can therefore get the following straight line graph. Now the gradient is going to be equal to the negative of a, so it's going to be the negative of the power term in the original equation, which is multiplied by the x term. So our gradient here is minus a. That's very important when you want to find the value of an exponential of the power term in this particular equation. We can also see that c is equal to natural log k, so therefore our y-intercept is natural log k. Now this can be done for any equation which contains an exponential term with an e in it, and we call this a log linear graph. Now you can also use any power law as a log-log graph. So let's think of the equation y equals kx to the power of n. Now you should take log base 10 of both sides. There's no e in this, so don't use natural log. So log y equals log k x to the power of n. We can then use the previous logarithm rule, as we mentioned before, to separate out this multiplication term. So log y equals log k plus log x to the power of n. We can then use another previous logarithm rule to separate it out further, because there's a power there. So we can say log y equals log k plus n log x. We can then think of this as a y equals mx plus c equation, which means we get a nice straight line graph. So we can say y is log y, log k is minus c, m is n, and log x is x. So once again, the gradient is going to be equal to the exponential, the power term in this particular equation. So if we have log y on the y and log x on the x, as shown here, this tells us that the gradient of the line will be n, so gradient is equal to the power term of this particular equation, and we also, the y-intercept is going to be log x. So again, this can be done for any equation which log k, sorry. So this can be done for any equation which contains an exponential term, and we call this type of graph a log-log graph. So we can summarize the different relationships in the graphs as below. So if it's a y equals mx plus c graph, you graph y against x, the gradient is m, the y-intercept is c. If you have a y equals ax to the power of n, you can plot natural log y against natural log x, or log y against log x. The gradient would be n. The y-intercept would either be natural log a or log a, depending on which log you used. And then if you have y equals a e to the power kx, you plot natural log y against x. The gradient will be k, so yeah, it will be k, and then the y-intercept will be log a, and you can work out terms from this. So here's examples of data plotted in a linear graph and in a log graph. So you can see here the gradient of this graph will give n, which is the power of the value on the x-axis, which in this case is t. So this links in, because if we worked out the gradient, we could see that the gradient is equal to 3.95 over 2, which is 1.98, which rounds to 2. And this makes sense in the equation. It allows you to work out what the power of the exponential will be, because we know the link is s is equal to 1/2 at squared. It's one of the Suvat equations, but it proves mathematically that t is squared because the gradient of the line is equal to 2. Here is an example of data plotted in a linear graph and in a natural log time graph, as shown here. This relationship shows exponential decay. Now, as we mentioned earlier, in an exponential relationship, the factor of change between the values is constant, i.e. over a fixed time, the value will double or the value will halve. Now, this can be proven on this graph, on the normal y-x graph, because values can be taken and the factor of change is then calculated between a fixed time, and if it is an exponential relationship, the value will be constant. So in this particular example, if we did between t equals 0 and t equals 4, well, the change goes from 0, it is 10, and at 0.4 it's 5, so it's 5 over 10, which is 0.5. Then you do between the same time interval, 0.4 and 0.8, it's 2.5 over 5, Again, it's going to be 0.5. You keep working it through. Each time you get 0.5 out. So we can see that because it is the same value each time, it's an exponential relationship. You can also prove it in this graph as the gradient is the factor of change, and so therefore should give a straight line if it is an exponential relationship. And again, the gradient will give you the value of the exponential, the power with respect to either e or to 10. So again here, the gradient is equal to minus 2.3 over 1.16, so therefore it's equal to minus 2.0. So if we put that into the equation, we can say I equals I0 e to the minus 2t. So again, we can then also find what I0 is, because the y-axis is equal to natural log I0. So if we then take the anti-logarithm of the y-intercept value, this will give you the value of I0. So because the natural log I0 equals 2.3, we can remove that natural log, do the anti-logarithm, we get I0 to be 9.97. So with that, that brings an end to our revision session today on the practical skills required for A-level physics paper 3 for in terms of all the different practical components of that first paper. Thank you so much for listening to this particular revision session. Have a lovely day.